Here we have the third example of drawing root locus. GC is again equal to KP, and GP is equal to 15 divided by S times S plus 3 times S plus 5. And we want to draw the root locus for different values of KP for this system. So if we want to rewrite it, to rewrite this GC times GP in the format that we want, in the format that we use as the default one, we have 1 plus rho times n divided by ds, which will be equal to 1 plus kp times 15 divided by s times s plus 3 times s plus 5. And accordingly we will have 1 plus 15 kp times 1 divided by s times s plus 3 times s plus 5. And from here we can say that rho will be equal to 15 times kp and we will solve 1 plus rho times 1 divided by s times s plus 3 times s plus 5. So we will draw the root locus for this equation. So for this example, we see that we have 3 poles, n is equal to 3. So we will have 3 open loop poles, accordingly 3 branches for positive locus and 3 branches for negative locus. M is equal to 0. We don't have any finite zeros of the open loop system. And accordingly n minus m, which is r, is equal to 3, which means that we will have 3 asymptotes. For which we need to determine where they cross each other, where they touch the real axis, and what is the angle for those 3 asymptotes. So we will have 2 graphs, again one for the negative locus here, and another one for the positive locus. Since we have 3 asymptotes, let's start by finding the xa for those asymptotes. If you remember, it is equal to sum of zi's minus sum of pi's divided by n minus m. We don't have any zero, so it is 0 minus sum of pi's. We have 3 poles. For the first one, we have P1 equal to 0, P2 equal to 3, and P3 equal to 5. So we will have here 3 plus 5 divided by 3, which gives us minus 8 over 3, which is equal to minus 2.66 almost. On the other hand, we need to determine the angle of the asymptotes as well. So we have r times kCa equal to 2h plus 1 times pi, where h will be equal to 0, 1, and 2 for positive locus, and 2h pi, again h equal to 0, 1, and 2 for negative locus. And accordingly, r is equal to 3. Kc of a will be equal to, replacing h equal to 0, 1, and 2 and dividing by r, which is equal to 3, we will have pi over 3, 3 pi over 3, which is pi, and 5 pi over 3 for positive locus. For negative locus, we will have 0, 2 pi over 3, and 4 pi over 3. This is for negative locus. Then we can just draw this asymptotes. So here this is XA. We can draw the asymptotes on the graphs. Before doing that, let's determine the location of the poles that we have. So we have one pole at the origin, another pole at -3, and the other one at -5. So here we have -3, -5, again here origin, -3, and -5. For the asymptotes, they meet the real axis at -2.66, which I assume it's here, XA. For the case of positive locus, we will have 3 asymptotes. The first one with the angle of pi/3. So I assume that this will be one asymptote. The other one with the angle of pi, and the third one with the angle of 5π/3. In the case of negative locus, we will have one asymptote with the angle of 0, the second one with the angle of 2π/3, and for the next one we will have 4π/3 as the angle. Now we need to determine which are the parts of the real axis which belong to the root locus for both PL and NL. So considering the real axis, again for positive locus, we should take into account the parts of the real axis for which we have odd number of zeros and poles on the right hand side. By looking at the position of the poles in the case of PL, we see that the range from -3 to 0 and the range from -infinity to -5 would belong to PL, yeah? Because we have odd number of zeros and poles. So we will have -3 and 0 combined by -infinity and -5. And for negative locus, since we need to have even number of poles and zeros on the right hand side of the test point, we will have a region from 0 to +infinity, and also from -5 to -3. So it is from -5 to -3, and from 0 to +infinity. Okay, so I will use this red color to determine these parts of the root locus which belong to parts of the real axis which belong to our root locus. Here we will have it, and this is another section. And in the case of PL, this will be the sections of the real axis which belong to our root locus. So in the case of negative locus, the branches will start from the poles. One of them will start from the pole at the origin, and it will go towards +infinity. And the other two will start at the poles, they will go towards each other, and at some point they will depart the real axis and will go towards the asymptotes. In the case of positive locus, one branch will start at -5, it will go towards -infinity, and the other two branches will start at 0 and -3, they will go towards each other, and at some point they will depart the real axis and they will go towards the asymptotes. Now we need to determine what are these breakaway points. So we need to determine the breakaway points breakaway points. And you know that in order to obtain those points, we need to solve this equation, n prime d minus d prime n, and we need to set it to 0. We already know that n is equal to 1. Accordingly, n prime is equal to 0. On the other hand, d is equal to s times s plus 3 times s plus 5. And if we just simplify it, we will have s times s2 plus 8 s plus 15. So we will have s3 plus 8 s2 plus 15s. This is this, and accordingly d prime is equal to 3s2 plus 16s plus 15. If we replace these expressions into the original equation that we have, we will get minus d prime 3s2 plus 16s plus 15 times n, which is 1, and we should set it to be equal to 0. So we need to solve this equation. 3s2 plus minus. Yes, plus 16s plus 15 equal to 0. And if you solve it, we will obtain s1 and 2 equal to minus 8 plus minus square root of 19 divided by 3, which will give us minus minus 4.12 nearly, and the other solution will be equal to minus 1.21. So these two will be the answers to the equality that we have: 4.12, 1.21 with the negative sign. And if we go back to the root-locus plot that we have on the real axis, we can see that minus 4.12 belongs to negative locus. So it is somewhere around here. Minus 4.12. And minus 1.21 belongs to the positive locus, which is somewhere around here. Now we can say that the branches will start from the poles. For the case of negative locus, they will start from minus 5, minus 3, they will go towards each other. And at this point, which is the breakaway point, they will depart the real axis and they will go towards the asymptotes. So if I draw the complete root locus by red color, we will have these branches going towards infinity along these asymptotes. And in the case of the positive locus, we will have the similar situation. So here the branches will depart at minus 1.21. And as you can see here, the branches will go towards infinity. Okay, this is not a very nice one, I would say, but yeah, in any case, we will have two branches going towards infinity along with the asymptotes. So in the case of positive locus, determining these points in which we have crossing of the branches with the imaginary axis is important as well, because those points determine what are the values for the KP or for rho, after which we will have instability. We can find the value for them using the amplitude criterion. So if you remember, amplitude condition is like this. N divided by D should be equal to the amplitude of -1 over rho. Okay, so this will give us the value of rho in which we have that condition. But prior to that, we need to determine what are the values of amplitude of N and D over there. Yeah? So we can find the value of rho using another method as well. We will see what will be the answer for this, let's say, condition, for the amplitude condition at that point. But prior to that, let's see what is the question that we have for this example. We need to find the range of values of Kp such that the closed loop system is bistable. This will provide us the answer for the previous point as well. Okay. So if you want to figure out what are the values for which our system is bistable, we need to again write down the equation that we have, the characteristics equation, d plus rho n equal to 0. And then substituting the values that we have, we will have S2, S3 plus 8, S2 plus 15 plus rho equal to 0. And if we construct the Ross table for this equation, so here we have S3, S2, S1, and S0. We just put the values that we have. 1. Here we have 15S actually. So 1, 15, 8, rho, and then the value for here. For S1, I would call it S10. We can just calculate it by the equation that we have here. Rho divided by 8. And at the end we will have rho for that. Actually we will have, if you solve it completely, let's do it. We will have minus rho plus 15 times 8 divided by 8. So we will have 15 minus rho divided by 8 here. 15 minus rho over 8 and rho for the last element. And if we want to have our system bistable, we need to have all the components in the first column of the Ross table to be positive. Yeah? So we need to have rho bigger than 0 and 15 minus rho divided by 8 bigger than 0. This tells us that rho over 8 should be smaller than 15, or in other words, rho should be smaller than 120. So we need to have rho bigger than 0 and rho smaller than 120 in order to have the bibo stability for our system. And rho equal to 120 would be the point at which our branches cross the imaginary axis. And accordingly, we can find the values for Kp as well, because we know that Kp is equal to 200 times rho. Or, the Kp times 15 is equal to rho, sorry. Yeah. So Kp, rho is equal to Kp times 15. And accordingly, for Kp, we can find the range Kp between 0 and 120 divided by 15, which is equal to 8. This will be the range of values for Kp in which we have our pi-ball system stable. Now we can determine what will be the value of the omega here. I call it omega because in this case our poles will be pure imaginary. So we will have s equal to j omega right here. Okay. So our s is equal to j omega, and we already know the value of Kp as well, or the value of rho. We have obtained it. Rho is equal to 120 at that point. So we can write the characteristics equation ds plus rho times n equal to 0, and d is equal to s3 plus 8 s2 plus 15 s plus rho equal to 0. Replacing s with j omega, we will have j omega to the power of 3 plus 8 j omega squared plus 15 j omega plus 120 equal to 0. Rewriting it, we will have minus j omega 3 plus 15 j omega plus 120 minus 8 omega 2 equal to 0. And since it's a complex value, we should have each part equal to 0. So from here we can say that either omega is equal to 0, which is their solution for this part but not for the real part, so this is not a acceptable one. Or we need to have omega 2 plus 15. So omega 2 plus 15 equal to 0, and accordingly omega will be equal to square root of 15. So going back here, in this point omega will be equal to square root of 15. Alright, so this is all for our example number 3. Please again don't forget to send me what you get for the root locus using MATLAB.